Hi everyone, I'm Luz Angela Garcia, a postdoc fellow at Universidad EXI in Bogota, Colombia, and I'm gonna talk about some recent work that I recently submitted. It is called The Properties of High Redshift Galaxies, and it's a theoretical work made with high resolution hydrodynamical simulations. And I want to start by thanking the organizers of Cosmology from Home 2021 for allowing me to share this work with you. So the first thing we need to know is that we're going to focus on the Epoch of Reionization, this era of the universe where the first stars, galaxies, black holes, quasars, and other structure form in the universe. And this is a period that goes more or less from redshift 15 to redshift 6. There are plenty of different evidences that the reionization was fully completed at redshift 6. And this period is basically characterized by the fact that the neutral hydrogen in the IgM or intergalactic medium turns into its ionized state due to the ionizing fronts produced and released by these stars and galaxies that are forming in this period. At the end of the reionization, the hydrogen, it's mostly ionized, 99% it's ionized, and those are this is the moment where we can actually start seeing the galaxies and the structure that has formed. We know that the main drivers of reionizations are galaxies, and there are also different observations that allow us to set up some boundaries on which are the main drivers. Now we know, thanks to observations with the Hubble Space Telescope, that the main drivers are mainly faint galaxies that are unobservable to this point, and large galaxies and bright galaxies are contributing, but in a lower proportion, since they have, or they show a large proportion of cell shielding that doesn't allow the radiation to escape. And because of that, we know that they don't contribute in a large proportion to this amount of energy that ionizes hydrogen. In here, I'm showing this connection that it has been established in different ways. So we know that the seeds of these overdensities that lead to the formation of galaxies and the structure in the universe was set during inflation, and the CMB, the cosmic microwave background, it's a result of this process. So regions in red are a bit has a million of Kelvin above the level of the CMB temperature, and the blue regions are colder compared with that average temperature. In those places is where we found these overdensities that lead to the formation of galaxies, and that's what we have in the picture in the left for the projected overdensity, and then we have the temperature that is shown in this yellow to purple different regions. And in these places, we know that where the density and the temperature is above the average, we're going to have the formation of most of the sources that produce the reionization. So in order to study the formation and evolution of these galaxies in the tail of reionization, I'm going to use some high resolution hydrodynamical simulations based on a model of Big Gadget 3 that includes self-consistently the star formation and metal enrichment. I'm assuming a flat lambda CDM model with cosmological parameters from Planck 2015, two different prescription for the wings. The feedback is given by either momentum or any different wings, and all the simulations have been run from redshift 8 to redshift 4 with a snapshot gaps of 0.4. And in addition to that, we have to account for 3 different box sizes, the 12 co-moving megaparsecs over H to the 25 co-moving megaparsec over H. And the fiducial run is the first one that I'm showing in that table, which has a box size of 18 megaparsecs, a co-moving softening of 1.5, and it doesn't include molecular cooling. And this is the one with momentum-driven wings. In addition, I gotta say that the simulations have been run with initial conditions at redshift 125. As I said, they contain feedback prescriptions, they implement metal enrichment in a self-consistent way, and they account for molecular cooling. So the first result I want to describe is the halo mass function versus the halo virial mass. And what I have here is the results with the fiducial simulation at redshifts 8 and 6, when we know that reionization has been completed. And I'm comparing with the same feed given by Baruzzi 2020, which is the model called universe machine. His simulations has been tested and constrained at different redshifts, whereas this simulation that has this redshift range where reionization is concluded and well, it's completely ended. Although our redshift range is much lower, you can see that our models are consistent with a powered low slope of -2 at this redshift range from 8 to 6. And that's consistent with the models from the universe machine. In here, I'm showing the halo occupation fraction, again at redshift 8 and 6. And in here, it's important to show that at redshift 8, the halos are completely occupied by stars in collapsed systems for a range of 210 to the 1029, and also that value is above the resolution range that we have in our simulation. That peak moves to 310 to the 9 solar masses for the halo mass at redshift 6. And as we can see, the halos are mostly occupied from masses to 10 to the 9 to 10 to the 11, which is actually the region where the systems are well defined and resolved. And above 10 to the 11, we cannot count with these observations since we know that there are just a few cases of galaxies in these small boxes. And here I'm showing the simulated galaxy stellar mass function. I'm using the The Schechter function proposed and shown in the first paper that I'm showing in this table, and the parameters fit by Bata Beukar in 2019, Gracia in 2015, and Duncan in 2014 at redshift 6, 7, and 8. And I'm showing the theoretical predictions from our models to these observations, and also I'm showing data from Song in 2016 and Gonzalez in 2011 at redshift 8, 7, and 6 from left to right. And in all the panels, we can see that our models are inside the regions defined by the simulations, and also are in well agreement with the three different fits proposed in this work, which is actually really reassuring, because initially these simulations were thought and proposed to describe the IgM and not necessarily the properties of the galaxies and the star formation rate that was occurring inside the galaxy. This plot tells us a different story. It's the galaxy stellar mass to halo virial mass function. It's showing in the x-axis the halo mass, and in the y-axis the stellar mass for each galaxy in our simulation. And again, I'm comparing results from redshift 8 and 6. The first one in blue stars, and the second in light blue, and the second one with dark blue. And I'm comparing with different stellar functions from 10 to the minus 1 to 10 to the minus 4, from top to bottom. And what I want to highlight here is that the galaxies in the simulations are mainly follow a trend of 10 to minus 2. So halo masses are at least 2 orders of magnitude larger than the stellar mass in galaxies in these simulations. However, for the high mass end, we have that this trend moves to 10 to the minus 1. So we gain at least 1 order of magnitude in the difference between the halo mass and the stellar mass. And this is consistent with other sets of simulations as the Renaissance or Astreus, but it differs at least in an order of magnitude with a universe machine that were used as a comparison, and I'm showing the results in red and dark red. Still, our simulations are in most of the cases well resolved and show this trend inside simulations. An important thing in this when we resolve galaxies, in particular at redshifts that are not accessible directly through observations, is to derive cosmic star formation rate that goes according to the observations. And that's exactly what I'm showing in the left. I'm showing the different observations that have been made with UV and AR and from Maddow and Dickinson 2014. And on the right, I'm showing the results with different sets of simulations, and also with the sets of simulations of this work and different observations. And as you can see, we have a difference of 1 dex in both cases, the observational case and also from our simulations, going from redshift 8 to redshift 4. When we take the stellar formation rate ratio, as shown here, and it's compared with Peruzzi 2020, we see that our simulations are mostly flat around this ratio and 0.4, whereas there's a clear trend, increasing trend for Verusi 2020. And this seems to indicate that the number of luminous galaxies in our simulations is not evolving in a large proportion from redshift 8 to 4, whereas the result from Verusi seems to be more in agreement with what we have seen from observations and direct observations. Finally, the chemical enrichment, which is driven by the star formation rate, is shown here, and it's mainly due to the model that it's set for the star formation rate, the initial mass function, which in this case, we're assuming a model from Xavier 2003 that accounts for intermediate and large masses for the stars. And also it's depending on the stellar yields in our models. So mainly from this multi-gas metallicity plot, what we can see is that the chemical enrichment is mostly driven in the star-forming regions, and then it moves outwards due to shock-heated gas outwards from the galaxies, and it populates the CGM and IGM. And this is mostly with SPEC with these feedback processes and wings. And of course, voids are not chemically enriched. This is the prediction. It's only a theoretical prediction from our models, as you know. There are no observations, direct observations of the cosmic mass density of given elements, but instead we have the cosmic mass density of particular ionized states. In this case, what we're getting is the theoretical prediction from our simulations. It can be used to constrain different observations in the future. So the takeaway messages from this talk is that we're studying the evolution of galaxy properties at the end of reionization. Our models agree with observed galaxies' stellar mass functions at redshifts 8, 7, and 6, and also with the cosmic star forming rate from redshift 8 to 4. The results are consistent with both their theoretical models as Renaissance, Strauss, Brock, and universe machine. And using these constraints from the universe machine, we infer a constant power law slope of -2 at redshifts 8 and 6. And this last conclusion will be tested in the future with the Hubble, with the James Webb Space Telescope. Thank you very much. And if you have any questions or further comments, please don't hesitate to reach me in my email or my Twitter account. Thank you.